Training versus inference, two phases of artificial intelligence that power everything from ChatGPT and Gemini to self-driving cars. But they're completely different processes, requiring vastly different types of computing power. In the next few minutes, we'll explore what makes them unique and discover the specialized chips designed to dominate each phase. Let's dive in. Training is the intensive process of teaching an AI model. Imagine feeding a neural network millions of images of cats and dogs over and over again, adjusting billions of parameters until it finally learns to tell them apart. This process can take weeks or even months. Modern foundation models like GPT-4 cost millions of dollars to train, but here's the key. This massive expense only happens once per model. The NVIDIA H100 GPU delivers up to 4 times faster training compared to the previous generation, making it the workhorse for companies building cutting-edge AI. Training is all about raw, parallel power, thousands of GPUs working together to process enormous datasets. But once training is complete, the model is ready for its real job, inference. Inference is when a trained AI model actually works. Every time you ask ChatGPT or Gemini a question, use voice recognition, or see a product recommendation, that's inference happening in real time. Here's what makes inference fundamentally different. While training is a one-time cost, inference costs compound with every single user interaction. And as AI scales to billions of users worldwide, those costs add up fast. Today, inference accounts for 80 to 90% of all AI computing power, and by 2030, it's expected to dominate 90% of the market. The good news? Inference costs have dropped more than 280-fold from 2022 to 2024, thanks to massive improvements in chip efficiency. Inference is all about speed, latency, and energy efficiency. Users expect instant responses, so every millisecond counts when you're serving millions of requests simultaneously. Let's talk about the chips powering this AI revolution. First up, GPUs, or graphics processing units. Originally built for gaming, GPUs became AI's foundational chip because they excel at parallel processing, running thousands of calculations simultaneously, which is exactly what AI needs. NVIDIA's H100 GPU with 80 gigabytes of memory and 4th-generation tensor cores can handle most AI workloads from 7 billion to 70 billion parameter models efficiently. It's the Swiss Army knife of AI chips, versatile enough for both training and inference. But NVIDIA didn't stop there. The new Blackwell B200 represents a generational leap, 3 times the training performance and 15 times the inference performance compared to the H100. In real-world testing, the B200 is up to 57% faster for model training. GPUs remain the gold standard for training because their general-purpose architecture handles diverse model types and allows rapid experimentation. If you need flexibility, GPUs are your best bet. Next, Google's secret weapon, TPUs, or tensor processing units. Unlike GPUs, TPUs are custom chips designed specifically for AI workloads. They optimize for tensor operations, the core mathematical operations of neural networks. And increasingly, they're focused on high-speed inference at massive scale. Google's latest Ironwood TPU v7 is a powerhouse. It delivers 10 times peak performance over 5P and 4 times better performance per chip for both training and inference compared to the previous generation. Here's where it gets impressive. Ironwood scales to 9,216 chips, delivering over 42.5 exaflops of compute power. That's more than 24 times the world's largest supercomputer, all optimized for the age of inference. And efficiency? TPUs are 3 times more energy efficient than NVIDIA's H100 for inference tasks. This makes them ideal for Google's billions of daily search queries, translations, and AI-powered features. TPUs prove that when you control the full stack, from chip design to software, you can achieve remarkable efficiency gains. Now let's talk about the most radical rethinking of AI chips, LPUs, or language processing units. Founded by Jonathan Ross, who originally invented Google's TPU, Groq built the LPU from scratch to do one thing exceptionally well: inference at lightning speed. Traditional GPUs inherited architectural baggage from graphics processing, complex caching systems, dynamic scheduling, all designed for gaming, not AI. LPUs eliminate these bottlenecks entirely. The numbers are stunning. Groq's LPU delivers over 5 times faster and more cost-efficient inference than traditional GPU systems. In public benchmarks, they achieved 185 tokens per second, up to 18 times faster than competing cloud providers. How? LPUs use hundreds of megabytes of on-chip SRAM instead of slower HBM with deterministic scheduling that eliminates latency unpredictability. The result? Time to first token of 0.22 seconds. Responses appear faster than humans can read. And they're 10 times more energy efficient than GPUs from an architectural perspective. LPUs represent the future of specialized inference chips, trading the flexibility of GPUs for pure speed optimization. So, what's the fundamental difference between training and inference that drives this chip specialization? Training prioritizes throughput, processing massive batches of data in parallel across thousands of chips. A few extra seconds barely matter when you're training a model over weeks. Training needs raw parallel power, massive memory, and flexibility to experiment with different model architectures. Inference prioritizes latency. Users expect instant responses. Every millisecond counts when you're serving millions of requests simultaneously. Inference needs speed, low latency, energy efficiency, and cost per token optimization. This divergence is reshaping the entire AI chip market. The AI inference market is exploding from $106 billion in 2025 to $255 billion by 2030. Inference workloads are growing 5 to 10 times relative to training as billions of users interact with AI daily. GPUs remain dominant for training because of their versatility, but for inference at scale, specialized chips like TPUs and LPUs are proving their worth through superior efficiency and speed. The trade-off is clear. Do you need flexibility for experimentation or maximum efficiency for deployment? The answer determines which chip you choose. As artificial intelligence shifts from the training era to the inference era, chip specialization is accelerating. GPUs remain the versatile workhorses, perfect for training, capable for inference, and flexible enough to handle whatever new model architecture comes next. TPUs balance both workloads with superior energy efficiency, giving Google a competitive edge as they serve billions of AI interactions daily. And LPUs push inference speed to new extremes, showing what's possible when you design silicon specifically for one task and nail it perfectly. The race isn't just about raw power anymore. It's about the right tool for the right job. As AI becomes ubiquitous, understanding these differences isn't just technical knowledge, it's understanding the infrastructure powering our AI-driven future. If you found this helpful, subscribe to the channels for more deep dives into AI infrastructure and technology explained. Training teaches the AI, inference puts it to work, and the chips, they're evolving to specialize in each.